Hi everyone. So in this video we're going to talk about arterial blood gases in different pathological scenarios. And so the arterial blood gases that we're going to focus on are PaCO2 and PaO2, which are respectively our partial pressure of carbon dioxide and oxygen in the arterial blood. Because the first case we're going to talk about is hypoventilation. So in a hypoventilation, what happens is our alveolus is getting less oxygen. So our minute ventilation goes down, minute V goes down, our alveolar ventilation goes down, or V dot A. So V dot A goes down. And if our ventilation goes down, obviously we would imagine that our carbon dioxide, which is being produced, is going to increase, and our oxygen is going to decrease. And so how does this manifest? Well, remember our carbon dioxide concentration at equilibrium is going to be determined by our production, V dot CO2, and that's going to be equal to 1 over K times PaCO2 times the minute ventilation. What this is saying is that every breath we breathe out, our minute ventilation, every breath that we take, is going to be fully saturated with our arterial carbon dioxide levels, right? Carbon dioxide is equilibrating between our arteries, our pulmonary arteries, and the alveolus. And so every huff out that we take is going to be huffing out that much carbon dioxide, the equilibrated concentration of carbon dioxide in the alveolus, which is the same as the carbon dioxide in the blood. And so since we have an equilibrium between those two, we can say that, okay, whatever carbon dioxide we produce has to be equal to the carbon dioxide that we let go, and the carbon dioxide that we let go is the PaCO2 times our alveolar ventilation. And so this expression basically tells us that our PaCO2 is fixed by these two quantities if we have a given amount of production of carbon dioxide and a given ventilation rate. Okay, so if our minute ventilation goes down and our VA goes down, and we have the same production of carbon dioxide, then our PaCO2 is going to go up. Okay, and so our PaCO2 goes up. That's easy to see. PaCO2 goes up. And our oxygen, our PaO2, now remember that's also going to be related to our minute ventilation, right? If we have more ventilation, we're going to increase our arterial oxygen. And so we can say that our P-alveolar O2 is going to be equal to, remember our alveolar gas equation, it's going to be, basically related to our FiO2 times PATM minus PH2O minus PaCO2 divided by the respiratory rate. And so what we can see here is that if our PaCO2 goes up, then our P-alveolar O2 is going to go down. And if we have a preserved AA gradient, which means that the gradient between our alveolar big A oxygen and our arterial little a oxygen, if that gradient is preserved, there's no problems with the diffusion across this membrane here, then what that means is that if our PaO2 goes down, big AO2 goes down, then our P little aO2 is also going to go down. So I'll put that up here. P little aO2 is going down, and our AA gradient is the same. Okay, so that's the response to hypoventilation. Okay, so now let's talk about another case. Let's talk about dead space. So in the case of dead space, we have one alveolus which is getting well perfused and well ventilated, and we have another alveolus over here which is getting ventilated but it's not getting perfused. So this could be an example of a pulmonary embolism, so that could cause a dead spacing. It could also be just anatomical or physiological dead space based upon, suppose we're taking really shallow breaths and we're not really, filling up our alveoli that much. Our alveolar ventilation is low because we have increased dead space in our breathing. So this is going to be our dead space. Now, if you remember, if we keep the same tidal volume, if our dead space goes up, then if our VT stays the same, we have the same tidal volume, we're taking the same size breaths, or we have the same minute ventilation, then our VA is also going to go down again. That's kind of the effective dead spacing. The effective alveolar ventilation, right? This is not really effective ventilation. This is effectively dead space. So our actual VA, which is our alveolar ventilation, is going to go down. And so the effect is going to be almost the same as our hypoventilation case, right? Our PaCO2 goes up. Our our P big AO2 is going to go down. Now our P little AO2 is going to go down, but in this case there's also another effect. And the other effect here is that now we have to send all of our blood flow through a smaller number of alveoli, right? So all of our blood, and now our blood is not able to go into, not able to travel to these alveoli. So all of our blood is having to travel through a smaller number of alveoli, which means that there is a lower diffusion time, the amount of time that they have, right? If they're jetting past this alveolus, there's more blood kind of coming through here. This alveolus might start to get overloaded. And so what overloading means is that our diffusion time, the time that they have for diffusion, is lower. So not only do we have a lower PaO2, P big AO2, not only do we have a lower alveolar oxygen concentration, we also have a elevated, I'm just going to write, our AA gradient has gone up. So if our AA gradient has gone up, that means our P little AO2 is going down significantly. So P little AO2 is going down significantly. Sorry, let me just clean that up a little. P little AO2 going down significantly. And so the overall effect is to have PaCO2 go up, PaO2 go down, and P little AO2 go even further down. And so that's the effect of dead spacing. Now, it's important to point out that if we hyperventilate in a case of dead space, so if we hyperventilate, we restore our VA back to where it was before, then that will slightly improve the situation here, right? Because our PaO2, so imagine now, let's say our response is to hyperventilate. Let's do it in purple. So hyperventilation. So if we hyperventilate, then what's going to happen is our VA is going to kind of get closer to normal. It's going to go up. Our PaCO2 is going to kind of come down, and our P big AO2 will come down, or will go up, excuse me. Now, the net effect of this, remember, the AA gradient will still be high. The AA gradient will still be elevated compared to normal. So our PaO2, our PaO2, it's kind of unclear what happens to our arterial oxygen concentration. But the bottom line is that we might see a decreased PaCO2, with hyperventilation, the hyperventilatory response, but our AA gradient will still be elevated. We can still know that there is some sort of strange physiology going on here because our AA gradient will be elevated, although we have this sort of compensatory effect, right? We're experiencing a low true ventilation rate, so we hyperventilate in order to compensate for that. We can bring our CO2 down and kind of restore, for instance, if we're experiencing the hypercapnia of having an elevated CO2, we can bring our CO2 down, but we still have an elevated AA gradient. But again, this might not manifest in having much different a change in our oxygen arterial concentrations, but we will still see this abnormally elevated AA gradient. Okay, the next thing that I want to talk about is shunting. So in the case of shunts, what we have is we have an alveolus here that is well perfused, well ventilated, and then we have an alveolus over here which is not ventilated but is being perfused. Okay, so we don't have any ventilation coming through here. Okay, so the effect here is, so remember, our CO2 concentrations in the blood, we have some CO2 in the blood over here and CO2 over here. And remember, we said that our PaCO2 was related to, I'll just say related to our V dot CO2 and our VaCO2. And in this case, if our, not VaCO2, just Va. In this case, if our production of CO2 is staying constant, which most likely it is, Now it depends. If our alveolar ventilation might change a little bit, right? If we have fewer number of alveoli, maybe we're not necessarily compensating for that. But overall, our alveolar ventilation will probably stay the same, right? If we have a few sort of shunted off alveoli, suppose we have some sort of consolidation in our lung, or if we have some shunting going on, our alveolar ventilation might not change. So our PaCO2 might actually be pretty normal in a case of shunting, unless there's some serious shunting going on. So our PaCO2 might actually remain normal. Okay, so what does that mean? That means that our PaO2, the amount of PaO2 that we see in here, is actually going to be relatively normal. So our Pa alveolar oxygen concentration might be normal. But what's happening is that now we have our alveolar oxygen concentration, so that's diffusing some into here, and we're getting maybe some normal diffusion on this side, but we're getting no diffusion on this side. We're getting no diffusion of oxygen on this side. And so now we got to talk a bit about what happens when we combine oxygen from our left alveolus and our right alveolus and get our sort of mixed arterial oxygen concentration down here. Right? So these two are going to kind of combine and into our main artery, our main sort of pulmonary vein, I guess, and end up in our arterial side. And so what happens when we mix these things? So remember, oxygen is not only dissolved in the blood, right? So I'm going to draw oxygens now as these little purple dots. So we have these oxygen molecules, and many of these oxygens are bound to hemoglobin, right? So there's hemoglobin here, and hemoglobin is carrying most of our oxygen. Most of our oxygen is kind of tied up in this hemoglobin. So that's our well-ventilated side, and on our not well-ventilated side, let's just say we have empty hemoglobin. And maybe there's like a little bit of oxygen. Okay, so now what happens? We pool all of our resources together. We have now a bunch of oxygen and a bunch of hemoglobin in our sort of combined area. And the question is, how does this equilibrate? How does this equilibrate? And the answer to that question is actually going to come from our saturation curves, right? Because overall, the total amount of oxygen that we have available to us is actually not, not really related to the dissolved content of oxygen. It's not really determined by the amount that's dissolved. It's mostly determined by the amount that is tied up in this hemoglobin. So if we wanted to figure out how much oxygen and how much hemoglobin do we have available when we combine all of this stuff, that's mostly going to be related to the amount of oxygen and the amount of oxygen bound to hemoglobin in each of these scenarios. So if we look at our oxyhemoglobin curve over here, we can see that we have a sort of sigmoid curve. And so on the right-hand side, we are riding very low on our sigmoid curve, and on the left-hand side, we're riding pretty high on our sigmoid curve. And in fact, let's say we're riding way to the right on our sigmoid curve here. So let's say we're riding way over here. So what's important to note is that we're not going to get an average of our two oxygen PaO2s, right? So we're not going to get just an average in the middle of our PaO2s. We're going to get an average of our saturations. So we're going to get an average of our saturations because, remember, we're pooling our resources. We're figuring out how much oxygen and how much hemoglobin do we have, and then we're going to kind of pool somewhere in the middle, and that's where we're going to equilibrate to when we pool all of our oxygen and our hemoglobin. So what that means is that our PaO2 is actually going to be much closer to our deoxygenated PaO2 than it is to our oxygenated PaO2, right? Especially if we're riding pretty high on our oxygenated side. And so our what we're going to see is we're going to see an elevated AA gradient. This is our A over here, this is our little a over here, and we're going to see an elevated AA gradient due to the averaging effect caused by this very, very deoxygenated blood and due to this sigmoid curve, which is really not helping us out. It's not even really giving us a true average between these two. It's telling us, okay, well, we have to, we're going to average the saturations, which is really, pulling our PaO2, lower. And this is mixing two alveoli, so it's, in many cases, it's not going to be a 50% shunt. We're not going to get 50-50 of deoxygenated and oxygenated blood, so, it'll be less extreme than this. But what is important to note is that our AA gradient is elevated, so our PaO2 is going to be lower. And what's different about this case, what's interesting about this case is that now imagine we start to hyperventilate. So if we hyperventilate, then what happens? Well, if we hyperventilate, our PaCO2 goes down. And you know that's not necessarily a important physiological effect, right? We didn't really have much acidosis to start with, but our PaCO2 goes down because we're trying to say we're stimulating our we're trying to get our oxygen back up, let's say, or we're trying to there are other systems that are stimulating our respiration rate. But what happens to our PaO2? So our P big AO2 is going to be increased. We're going to have an increased P big AO2. But what's that going to do? That's going to push us farther along on our hemoglobin saturation curve. But when we combine, we're still only combining the average of these two values. We're still only combining at the average of these two values, which is going to be at the same spot that we were before. So our P big AO2 goes up, and our AA gradient also goes up. The extent of our AA gradient also goes up. And so basically the overall effect is that our PaO2 remains low. And that's kind of the effect of shunting, which is that hyperventilation will not get us out of a shunt. Hyperventilation will definitely decrease our PaCO2. Our CO2 concentrations will start to decrease because remember, CO2 concentrations are directly related to our VCO2 and our alveolar ventilation, but our PaO2 is going to remain low in the case of a shunt. Okay, the last case that I want to talk about is a diffusion abnormality. So diffusion abnormality. So in this case, what we have is, let's say we have some sort of decrease in the surface area of contact of our alveolus and our blood vessels. So we have one alveolus that's like that, and maybe, let's say, even one normal alveolus, let's say. But overall, the effect is that we have a decrease in the surface area of contact between between our alveoli and our capillaries. So in this case, basically what happens is that we have an effectively increased, or we have an effectively decreased diffusion constant. So our diffusion constant is going down. And so basically what that means is if we have the same amount of blood traveling through here, it is not getting as well oxygenated as before. Because now, in this case, before it was able to get fully oxygenated in very, very rapidly. It was getting oxygenated very, very rapidly. So even before it was going through the full length of the alveolus, say, it was traversing along in this alveolus here, it was getting oxygenated by the time it got, 1/3 of the way along its path. But now, with a diminished diffusion constant, it's taking more time, right? It needs more time. Our diffusion constant K, or let's say diffusion constant decreases. So the amount of time that we need in order to kind of get fully oxygenated is now increasing. And this is usually not a problem at rest. Usually at rest, these hemoglobin molecules need more time to get fully oxygenated, but it's not really affecting much at rest. But what happens during exercise is that it's the same situation that we talked about above with the dead spacing where, well, this stuff is now moving along quickly, and now very quickly as we start to exercise, these hemoglobins are not getting fully saturated. So in this case, we have an increase in a diffusion constant increase leads to, again, we have a normal PaO2 here, because remember our diffusion constant increase is only for oxygen. Decrease in diffusion constant. Our carbon dioxide diffusion constant is basically the same as before. Carbon dioxide is very, very quick to diffuse through all this stuff, so it's not really being affected. So our PaCO2 is still the same, and our P big AO2 therefore is still the same, but our diffusion constant is making it so that our AA gradient is now highly elevated. So and that's just because again our arterial blood does not have time to get fully oxygenated in the case of especially in the case of exercise, where it's shooting through this sort of alveolus, and it doesn't have the time that it needs to get fully oxygenated. So our AA gradient is increased, and we have a decreased PaO2. And so what happens here with hyperventilation? So in the case of hyperventilation, again, our PaCO2 will go down, our PaO2 will go up. So actually, PaO2 will go up. And in this case, our AA gradient will still be the same as before. The AA gradient is going to be the same. So that's not going to change much. And so our PaO2 will actually be restored a bit. So if we have a diffusion abnormality, we will improve with hyperventilation, and we'll also improve if we give, say, some supplemental oxygen so that our PaO2 increases even further. But again, as I said, shunting will not improve with supplemental oxygen, right? Because if we improve our PaO2, big AO2, that's just going to lead to an even bigger increase in our AA gradient in the case of shunting. But supplemental oxygen can be used for diffusion abnormality, and certainly supplemental oxygen can also be used for our case of hypoventilation.